Welcome viewers to the second segment of the second lecture for the online series of lectures for the course of Dynamical Systems. Towards the end of previous segment, we stated Global Existence Theorem 1. In this segment, let us try to prove it first. So here goes the proof of Global Existence Theorem 1 or Proposition 2. Okay. So we are supposed to prove that the maximal interval of existence in the initial value problem 2, JP0 is the entire real line. Okay. By way of contradiction, let us first assume that JP0 is equal to A comma B such that B is finite. Okay. Now we use the growth condition or the growth assumption for assumption 4. Okay, which is what? Which is the condition for at most linear growth. Okay, so and that states the condition states that there exists non-negative constants C sub B and D sub B such that the norm of the vector field at the point Tx is bounded by this expression, the one that we are going to write now, C sub B plus D sub B times norm of x. This happens for all t in this closed interval minus b to plus b and for all x in Rn. Okay, so this was the growth condition in our context. So let us number this equation by 5. Now we already know that t0, the initial time, is contained in this maximal interval of existence, right? Now, without loss of generality, we assume that t0 is greater than minus b. Okay, so that this 5 will yield the norm of f of t comma x is bounded by C sub b plus d sub b times norm of x for all t in this interval t0 comma b, okay, which is a subset. This interval is contained in this interval, right? For all t in this interval and for all x in R to the n. This we number by 6. Okay. Now let u from this maximal interval of existence to the to r to the n be the solution to our IVP numbered by equation 2, we can then write u of t is equal to p0 plus t0 to t, the integral of f tau u of tau d tau. Okay, for all t in this maximal interval of existence. Okay, this guy is true for all t in a comma b, and hence it's also true for all t in this subset, okay, subset of a comma b. Okay, now it's important to note that here this expression, if you just differentiate it with respect to t, then using FTC, fundamental theorem of calculus, okay, tells that u prime t is equal to f of t of u of t. Okay, this is what we get, which was the fundamental differential equation for the initial value problem. Okay, and it is obvious from this integral representation of the solution of the initial value problem that if you plug in t0 in this expression, you obviously get u of t0 to be equal to p0. Okay, so indeed this integral representation represents the solution of our initial value problem. Okay, good. Now we will take norm on both sides of this integral representation and massage, and use triangle inequality to put it in a convenient form. Okay, let's try to do it. So let me write this integral representation of our initial value problem, which was this. F of tau u of tau d tau. Okay, and this is the case for all t in the subinterval t0 to b. Right. Now we take norm on both sides and use triangle inequality to find that the norm of u of t is bounded by the norm of p0 plus the integral from t0 to t, where in the integrand we have this norm of f tau comma u of tau d tau, and this is also true for all t in this interval, subinterval. Okay, so the norm ends here, and then this guy is equal to norm of p0. We're just substituting the growth assumption. Using the growth condition, we can rewrite this expression, okay, in the following way: C sub b plus d sub b times the norm of u of tau and I think there should be an inequality here. Okay, I should correct it in my notes as well. Okay, so and this leads to this for all t and t0 comma b. Okay, and this is bounded by norm of p0. The maximum value that t can attain in this in this integral is b, right? So this is again bounded by cb times b minus t0, okay, plus this is a constant that comes out of the integral from t0 to t, the norm of u tau d tau for all t in t0 comma b. Okay, this is what we number by 8. Okay. Now putting this guy to be equal to c0, putting c0 equal to norm of p0 plus cb times b minus t0 in equation number 8, one obtains norm of ut is less than or equal to c0 plus db times the integral from t0 to t, the norm of u tau d tau, okay, for all t in t0b. Okay, this is what we are going to number by 9. Okay, now we define an equation. Define g from the interval t0 to b to the set of real numbers by g of t to be equal to c0 plus db times the integral of u tau, the norm of u tau over d tau for all t belonging to this interval. Okay, this is our equation number 10. Okay. Okay. Now it follows from equation number 10, this equation, and from the fundamental theorem of calculus that this guy g is differentiable on the open interval t0 comma b, okay, with g prime t being equal to just db times norm of u of t. Okay, and this is going to happen according to fundamental theorem of calculus for all t in this open interval. Okay, we put equation number 11. We put this expression as equation number 11. Okay, so let me erase the top part. Okay. Now, nine and 10 together imply that okay, norm of ut is less than or equal to g of t. It's obvious from the experience, but this is how we assumed the right hand side, because we put the right hand side of 9 to be equal to the function gt, so obviously the norm of u of t is less than or equal to g of t. Okay, this is our equation number 12. Now 11 and 12 imply that g prime t is less than or equal to d sub b times g of t. This is going to happen for t in this open interval. This is equation number 13. This inequality is numbered as equation 13. Now, rewrite this differential inequality as g prime of t minus db times gt less than or equal to 0 for t belonging to this open interval t0 to b. We call it equation number 14. Now we multiply both sides of equation 14 by e to the minus db times t, to the power minus db times t. By this expression, we multiply both sides of equation 14 to obtain g prime t times e to the minus d sub b times t minus d sub b times gt times e to the minus d sub b times t is less than or equal to 0. Okay. Now we collect all the terms and use Leibniz rule to write this expression, the whole expression, as d dt e to the minus db times t g of t, and the differential coefficient of this guy is less than or equal to 0 for t belonging to this open interval. This is what we call equation number 15. Okay, good. I need to erase this part now. Okay, now integrating on both sides of the inequality 15 from t0 to t. will yield the following. So when we integrate this left hand side and substitute these two values, we end up with e to the minus dB times t gt minus e to the minus dB t0 g of t0 to be less than or equal to 0, and that will give us g of t to be less than or equal to e to the d sub b t minus t0 times g of t0, and this is valid for all t in this open interval. This is our equation number 16. Okay. Now remember the definition of g that was given by equation number 10. So let me write it for you here with a side note. G of t was defined as C0 plus dB times the integral from t0 to t, the norm of u tau t tau. Okay, and this was defined for all t belonging to this closed open interval t0 to b. Okay, so now if we take the derivative of this guy, then we get g prime of t to be equal to dB times norm of u of t, which was equation number 11. Okay, but we don't have to do it now. Just replace t0. So replace t with t0 to obtain, this will go to 0 then. G of t0 is equal to c0. Okay, so this is what we need to use. Now 12 and 16. 12 and 16 together imply that the norm of u of t is less than or equal to e to the dB times t minus t0 times g of t0, right? And this expression, by using this equality, can be written down as e to the dB times t minus t0 times c0. Okay, so we end up with this expression that is the norm of u of t is less than or equal to c0 e to the d sub b times t minus t0 for t belonging to for t belonging to this interval, right? So I should correct it in my notes as well. This is the open interval. Okay, good. This is what we number by equation number 17. Okay. Now I need some space. Okay, this is equation 17, and now set r sub 0 to be equal to this number c0 e to the db times t minus t0. This is a positive number. Set this positive number to be equal to r0. Okay. One can immediately see using 17 that u of t will be inside the closure of the ball around 0 of radius r0. Okay, this thing is r0. Okay, so ut must belong to a ball of radius r0 centered at 0. This is clear from equation number 17. For all t in this interval, right? t0 comma b. So it means that no positive epsilon can be found such that t belonging to this small interval will imply u of t does not belong to this compact set. This is of course a compact set from the definition of compactness in the Euclidean space, right? It's a closed ball around 0. So this result is in direct contradiction with the statement given in proposition 1, right? So let me erase this part now. This result is in direct contradiction with the statement given in proposition 1, which means that our initial assumption about B being finite was incorrect. Hence, B is infinity, right? So that the solution of the initial value problem, underlying initial value problem, is indeed a global solution. Okay. So this is how we prove proposition 2. Okay. QED. So now an important corollary to proposition 2. So let me erase everything. a very important corollary which restates proposition 2 using global Lipschitz condition. Okay. Corollary to proposition 2 which we call global existence theorem 2. So here it is statement of corollary to proposition 2. Let f from r to the n to r to the n satisfy the global Lipschitz condition, I'm writing this global Lipschitz condition now. Lipschitz condition, which is as follows: the norm of f of x minus f of y is bounded by k times the norm of x minus y for all x, y in r to the n. Let me call it equation number 18. Okay. Then for any initial point or initial value t0 comma p0 in r cross r to the n, the solution to the IVP dx over dt to be equal to f of x and x at t0 equal to p0. This is equation number 19, the initial value problem for this globally defined vector field exists for all t in the set of real numbers. Okay, so this is another version of global existence theorem in terms of global Lipschitz condition, which is this inequality. Let us prove this corollary. Proof. Okay, note that for any vector in r to the n, it follows from this global Lipschitz condition that it follows from 18 that norm of f of x minus f of p0, which is of course a vector, a point in r to the n, a fixed which we have in the beginning. Okay. The norm of this, the difference of these two vectors is less than or equal to k times norm of x minus p0, which yields norm of fx, which we write as norm of fx minus f of p0 plus f of p0, and by a triangle inequality this is less than or equal to norm of f of x minus f of p0 plus norm of f of p0, right? And this guy is less than or equal to, by using this inequality, norm of f of p0 plus k times norm of x minus p0. Okay, and again using triangle inequality for this summand, we get the whole thing is less than or equal to norm of f of p0 plus k times norm of p0 plus k times norm of x. This is equation number 20. This inequality we call 20. Now remember the condition of at most linear growth given by equation number 4. Okay, if you don't remember the equation, let me write it for you here. Okay, which was the norm of the vector field is less than or equal to Ct plus d sub t norm of x. Okay, this was equation number 4. Okay. So compare this growth condition with equation number 20 and see that in this context Ct can be taken as norm of f of p0 plus k times norm of p0, right? This is a strictly positive quantity. Well, yeah, this is a non-negative quantity of course, right? And of course k is a non-negative number, therefore dt in this, in our context, is equal to k, right? So therefore we have the condition of at most linear growth satisfied, and hence proposition 2 confirms that the statement of the corollary is true. Okay, so in other words, the corollary then follows from proposition 2. Okay, all right, QED. Good. So I think I'll take a break here, and in the last segment we'll study continuous dependence of solutions on initial conditions. Thank you for attending the second segment of the second lecture.